Okay. Okay. Good afternoon, ladies and gentlemen. Welcome to my session, where I'm going to talk about scalable applications for SharePoint. I know there's been many sessions that are in the same slot, very interesting, so thank you for choosing mine. I hope that you will learn useful things in this session. I know how hard is it to be in front of a developer audience, should be developer audience, because you are much brighter and smarter than I am, and you're a very difficult audience to satisfy. So I'll try to fulfill those expectations. My session is called 7 Tenets of Highly Scalable SharePoint 2013 Apps. I'm sorry I couldn't make it shorter, but the title is as descriptive as I could get it. Because the point here is that I'm not going to talk about normal SharePoint 2013 apps. I'm going to talk about highly scalable apps. So we will have to define what highly scalable means. And as we are talking about apps, so you know that now, as announced in the keynote, we have an updated API for Office 365, and we also have flexible tools and contextual application to build on. Now, my name is Edin Kapic, and every time I have to write my last name in a slide, I'm so grateful for Unicode support because of my last name. I'm sure that all of you with non-English names, you understand what I mean. I work for a company called Busy in Barcelona, Spain, in the sunny side of Europe, and we have built a social network, also called Busy, on top of SharePoint, on-prem. And we had to do this on a scalable way. And this session is partly because of the lessons that we learned the hard way. So I would like to share those lessons with you so you don't have to learn it the hard way. So, scalable apps. Scalable comes from scalability. And if we look up scalability in dictionary, scalability is the ability of something to handle an increased load. So in our apps, scalable apps are those apps that react to increased load without breaking in the process. This is the dictionary definition. I have an alternative definition, maybe easier to conceptualize. Scalable app is when you build your app in an Office store, a new shiny app that's going to sell millions in the Office store, and you deploy it. And then your colleague comes and says, I have good news and bad news. Okay, tell me the good news first. Well, the good news, we have 1 million new users. Good, it's selling like donuts. And what are the bad news? Well, the bad news, they all sign up tomorrow. Okay, and now, how do you face this situation is what defines whether your application is scalable or not. You have a gut feeling. So basically, if you have this face, then it's surely not scalable. Because you begin to think, oh my God, if I have more than 5,000 requests, it's going to break, and this and that, and the space. So you haven't planned for scalability. This is the phase we would like to avoid, right? And you have this phase, then you're good to go. Of course, I couldn't resist putting images of cats in a presentation, so I hope that you're going to pardon me for that. But beside the funny thing, what's hard about scalability is those errors, they do not appear when you are testing your application. When you develop and you test, you have a small load. And the scalability errors appear when your user load reaches a certain limit, the breaking point. Every app has its breaking point. And when you find the breaking point, it leaves a kind of bad taste to us developers, right? It's like we have put so many hours of hard work, and then it breaks when you have 10,000 users accessing your application. So it's much better actually to design for scalability beforehand, so it doesn't catch you unaware. And the other nuisance, personal nuisance, is that demoing scalability is a tricky thing because I I would have to build, I don't know, a dozen or 20 servers, deploy the app, make a realistic user load without repeated data, so actually to test the scalability, and it couldn't fit this session. So what I've decided is to show you bite-sized demos of key concepts around scalability. And what I hope you to take away from this are the concepts. Because how to implement those concepts, there are many sessions in this conference. I'm going to mention some of them at the end, so you can get pointers of how to actually do this. But I would like you to go away from my session knowing why to do this. Okay? So what happens when scalability fails? 2 years ago, I think a game was launched, official game for Simpsons series was launched on the major mobile app stores. And what happened? The server wasn't scalable. So millions of people downloaded the app, they launched the app, and they got this message. And they tried a couple of times, and they uninstalled, and they left bad reviews, and it really was a bad publicity for the maker of the game and the publisher of the game. They had to remove the application from the store, then publish it again, but it never lifted up again. So this is the kind of scalability we would like to avoid. What happens when scalability is awesome? A small team builds a game from 0 to 8 weeks, from 0 users to more than 5,000 users per second, 5,000 requests per second, and the latency goes from 0.5, storage latency, to 0.9. So this is the kind of scalability we are looking for. So we have this hockey stick user load, and the response time, sorry for that, should be as linear as we could get. It's never going to be linear, but it should be as flat as we could get. This is our goal. And I want you to build highly scalable apps if you are going to have millions of users or tens of thousands of users. Scalability is an overkill for small user load because it's much more efficient to write smaller and not as complex architecture. But if you want high scalability, there is no other way. So we are talking about SharePoint apps, not any apps. So let's do a quick recap of SharePoint 2013 application architecture. As you probably know, if there's anybody here who doesn't know about the new app architecture, I will be really surprised. The SharePoint 2013 apps are cloud-based, which means that they run outside SharePoint. So this is the mind shift from running your code inside SharePoint when everything is, let's say, close to you because you're running inside the platform, and now you're running outside the platform. So you have to think about things that you haven't thought about before, like how should I optimize the number of round trips and so on. We have two kinds of cloud-based applications. The first one are the the auto-hosted applications. I call them toy application because there is you can't do many things with it. Essentially, you get an IIS, SQL Azure, and that's it. So 2 problems with this. You cannot fine-tune. You cannot add additional services. It gets deployed. Every time a user downloads and installs your application, you get another instance disconnected from other instances. And more important thing, you cannot sell it. And if you cannot sell it, what use there is to have millions of users? And we have the grown-up applications, the provider-hosted applications. You run on your own data center, on Azure, on other cloud provider, whatever. So you bring your hosting infrastructure. So now you can leverage all the power of additional services in your scalable app. So the first thing to take away is do mind shift. SharePoint is another external system. You are not running inside SharePoint. So treat it as external web service or external database any other remote server. And if you allow me for a moment to go to galaxy far, far away to see what we can learn from Star Wars, I love that look. Like, what's he going to talk about? Well, I said we are on a good venue because on the floor below us there is a room called Lando. Yeah? So I'm not the only one to notice the name. Okay, good. There are many geeks in the audience. Good. Okay, so if you ask Master Yoda, he's wise to know about scalability, and he says that with a cloud, we have potential scalability. What does it mean? It's not guaranteed. When you deploy your app to a cloud, it's not automatically scalable. You have to architect carefully to use that for scalability, because it doesn't come out of the box. As much as we would like for the cloud deployment to be hassle-free, you still have to architect your app. And what happens when you architect with scalability issues? Well, we know how the designers of the Death Star fared. They built, the brightest minds of the galactic empire built a moon-sized battle station with all the latest and greatest technology and a single point of failure by design, reactor core. We know how it fared when a single X-wing fired a torpedo inside the reactor core. Boom. And the chief architect had a hard time explaining to the CTO why it failed. He didn't plan for failover, right? Okay. Now, back to our regular program, back to SharePoint. When we design SharePoint 2013 app, chances are that we think about this. We have a web role or a website inside Azure. We deploy our app. Our app has several logical layers and usually writes something to the data store, usually SQL Azure. And of course, it goes to SharePoint to query and update data. But what happens here is that we have multiple instances, but they're like separated from each other. This is simple. This is good for small apps. For a user load, it depends on the app, but you can measure. You can add thousands and thousands of requests and see when it breaks. And what I propose is another kind of architecture with a little bit more moving pieces. I'm going to cover them as we go. But what you see is that scalable architecture is more complex than non-scalable architecture. This is the price we have to pay. Nothing comes free in programming. We always have to trade off one thing or another. Okay, so the outline of my talk in detail is this slide. It has a small ribbon called summary, so if you want to take a photo of it to share with your colleagues. When I'm in the audience for a technical presentation, I really like one slide summary so I can talk about it back when I come to my colleagues. It's going to be repeated at the end, so don't worry. What I've done is I've organized all those hard lessons that we learned doing scalability along 3 guidelines, or the guiding principles, and then 7 implementations of those principles, 7 techniques, 7 tenets of highly scalable apps. So the 3 guidelines are avoiding round trips, which means don't go to the external service unless you have to. Avoiding bottlenecks, which means don't make one part of your application a bottleneck so that everyone has to wait or to experience resource contention. And of course, avoid single point of failure. It could be one machine, another machine, it could be even an external component, but avoiding single point of failure. So how this maps to our scalable architecture? Essentially, we reduce round trips using content delivery networks and using cache. We reduce bottlenecks by decoupling different tiers and using queues and using non-relational storage. And then we reduce single point of failure by duplicating and making redundant design. So this is how those 3 guidelines map to our architecture. So if you are ready, we are going to see the first guideline and the 2 tenets associated with it, which is avoiding round trips. The first tenet of avoiding round trips is cache. Everyone knows cache. Cache is the really cheapest mechanism you have to avoid round trips. And it's as simple as it can get. You read something from the external service, you store it close to you, and then you don't have to go again to the external service. You just read from the stored value. And with it comes a nasty feature called stale data. Because you are not going to check for fresh data every time you read, so chances are this data has changed. And you have to live with that to one degree or another. And the question is, from the business point of view, how much stale data you can have. I'm going to show you an example of a mechanism that you all know in a couple of slides. And it uses caching in a really efficient manner. There are two kinds of cache. What is? Okay. There are two kinds of cache mechanism available to you, using Azure or using any other technology. You have local cache, which sits in each machine or in each instance of the server or the service you are instantiating. And you have distributed cache, which is distributed among all the machines or all the services comprising your layer, your application layer. So local cache is small, but it's so close to the running code that it's super fast. And the guideline here is put small data, very frequently accessed data, and data as static as you can. For instance, you build an e-commerce application, and you have to deal with countries, cities, zip codes, things like that. They don't change from one day to another, even from 1 year to another. You can safely read them once when your application is instantiated, and you forget the data store. You just read from cache. It's small enough to be of high value. And what should you push to distributed cache? Well, the question is, why shouldn't you push anything to the cache? So it should be by default. You have to incorporate, to be scalable, you have to incorporate caching. And the sooner you think about caching, less problems you're going to have with caching. Because what happens, and we have all done that, and I also feel guilty of that, is that we add cache as an afterthought when we have developed our application, right? But it's wrong, because that's when we experience stale data and things that are not updated, and then we change another thing, and then it breaks another thing. So it's best to cache by default, and then treat non-cacheable data separately. I promised you an example of a service that uses caching effectively. DNS. You're all familiar with DNS, right? You have a domain name mapped to IP address, and sometimes when you change providers, you change the IP address, and it slowly replicates across the servers. Why? Because the browser has its own small cache here, and anytime you issue a request from the browser, DNS entry from the cache, from browser cache, is going to be used. If this address is not found, the operating system also tries to resolve DNS, and it caches the result. And if the operating system doesn't know what this value is, it's going to ask the internet provider or the gateway in your local network. And it also has a cache. And it goes all the way back to the original server where your DNS record sits. So DNS embraces caching. Without it, I think it would be unfeasible to do a distributed algorithm like that. So caching is not a scary thing. And the second thing to avoid round trips are the content delivery networks, the CDNs. CDNs are a thing that is used to cache blob data. So blob, or binary large objects, are data that you store as files or streams or documents, whatever. And Azure allows you to store blobs in a thing called blob storage. So what happens here is that many times you're going to read the blob, process it somehow, and return it to the user. But mainly, the processing of the blob is get a blob, put a header around it, and deliver it to the user. So in this case, what's good for you is to bypass the processing totally, which means that each blob, if it's public in Azure, has an associated address, IP address, or URL. And then you can just point the user or the client HTML to that address. You don't have to go to your app, to the server code, read the same blob, and then write a response. What happens when the blob is not public, such as a document that is only available to paying users? They have to enter the user and the password. Well, you can do the thing called shared signatures. Shared signatures is a thing that OneDrive uses when you share a link with someone. When you upload something to OneDrive, you say share, get a link, and this link has extra parameters in the URL, which basically encode the permissions for the user who accesses this file using the URL. And they also can be revoked, and they also valid for some time. And this is the same mechanism that you can use to ensure that your blobs can be offloaded from your application, because the user browser accesses them directly, and you take into account the permissions. So why I'm talking about blobs? Because CDN, Content Delivery Network, is a caching storage for blobs. It's a distributed network of servers run by Microsoft, in the case of Azure CDN, that acts as a cache. When a user from a single region accesses a blob from your application, this blob gets copied to the CDN. And the next user, the lucky one, gets this copy free, because it doesn't have to be served from the blob storage. You are saving one round trip. And the thing is, the first user pays the toll, and then all the others are free riders. So what should you offload as blobs in your application? Well, everything you can. Images, icons, JavaScript files, media files, whatever which is not runnable code or configuration files. So anything that is static, it looks like a file or image, go to blob. You are saving round trips. Your app doesn't have to do the shuttling of the bits from one place to another. And what happens with stale data, because CDN is a cache? Maybe you are changing the JavaScript, but the most of the users, they still have the wrong version. You can add an extra parameter to the URL, like referencing something.js and an extra parameter, and this acts as a versioned URL, because the CDN checks for the exact name. So if you add an extra parameter, even if it doesn't do anything, it's going to work. It's going to fetch this file directly from the blob storage. Okay? I'm going to show you the difference between accessing a blob from the server and accessing it directly. If the networks serve me well here, I'm going to switch to my machine. What I have here is a small app built in MVC, which has a home controller with a couple of actions. There are two actions that I use to display blobs. One goes to my Azure storage, gets a picture of Las Vegas. I can show you this is my Azure subscription, and I should have storage account. Just a second, it's getting, okay, it's here. And I have the blob storage. I have a container, public container called images. And inside images, I have one image, 2.5 megabytes. If I open it, it's going to be downloaded and displayed this. Okay. So what I'm going to do from the controller is I go to the blob storage. Okay, let's. Okay, this. I go to blob storage, get image, and get only the URL. And then I have another action which gets the blob, builds a memory stream around it, and returns it as a binary file, as an image. So two different ways to get the binary data from the blob. And what happens is that when I run this, under a load, which means that your application is busy, so I will just fire up a tool. I'm a big fan of Apache benchmark tool, AB. You see the letters in the shell, or I should make it a little bit bigger? Okay, just a second. 20. Okay. So I'm going to issue a request, like 5,000 requests, 100 concurrent requests to the home page. It's going to make our application a little bit busy. And in the meantime, I'm going to, it's issuing requests. And now I'm going to the demo page, and I'm loading in parallel. Oh, damn. The processed one took less than the unprocessed one. It depends on the network, but usually the unprocessed one takes shorter time to come to the user than the processed one, because you are saving one round trip. Because if I go here to see the unprocessed one, the URL is pointing to the blob storage directly, bypassing my application, saving one round trip. And if I go to this one, it's my app. So it's a server code. I'm getting one round trip. I have to go to the application and then to the blob storage. And with the unprocessed one, I'm saving a little bit of time. Okay. I'll leave this here. As I promised, I was building small bite-sized demos just to highlight the mechanism. And if you are interested in how to do all those techniques, there are many resources that can help you with it. So we are finished with the first guideline. The first guideline was avoiding round trips. The second one is avoiding bottlenecks. All those parts of our code that act as a bottleneck and they prevent requests from being fulfilled. The first one I've chosen is storage lock. Storage lock is basically when you go to an airplane and you go to a lavatory just to find a queue of people waiting in front of the door, and then you cannot access a storage resource of a kind because it's being used by multiple persons. It couldn't be shared. What happens when we use relational databases? We also have storage locks. When we use any kind of storage, we get storage locks because there is a limit to concurrent capability of storage system. But the interesting thing is that we are so familiar with the relational database model that we don't think of all the costs of scalability that it has. For an example, I want to model a customer with his address. So I have user related to an address related to city, and related to state. The data sits only in one table, on one place. It's consistent. It's normalized. There are no redundancies. And when I want to get information from the user and its address, the SQL server, in this case, has to match those entities, those tables, in a single view. What happens if I'm just changing the name of the user in that moment? Well, you've heard about isolation levels in SQL Server. Basically, it's the limit we put to concurrent requests. Usually, when we mix changing things and reading things, we get locking in the storage. We get locks. We have to wait until the change operation is finished, or it's committed or rolled back. On the other hand, we have another data model which is designed for high availability and scalability. It's called NoSQL, or not only SQL. It's also called document databases or key value databases. And in Azure, you have a kind of document database. It's not fully documented database. It's called table storage. It's highly available, much more than the SQL Azure, but it doesn't have any relationship between the entities. So basically, you have containers or collections of entities, which are basically collection of keys and values. So it doesn't even enforce the schema. So you can change the schema in every single row. You can add a totally different schema. It doesn't care. So we get high scalability, high availability, but we lose consistency. Well, a kind of. We lose immediate consistency. Immediate consistency means that every change that I make to my data is immediately visible to all the consumers of the data. In non-SQL databases, usually it's not the case. You could make for it, but usually you forego immediate consistency for eventual consistency, which means that the data is going to be updated eventually in a couple of milliseconds, couple of seconds, minute, doesn't matter. That's why when you tweet something, usually it takes a couple of seconds for that to be displayed in your Twitter stream. Because all the highly scalable apps, they use some kind of non-SQL storage because of the benefits for the sheer number of data that you can store inside. Okay. There is one thing in the database design called KAP theorem, which states, basically it has a lot of academic stuff, but basically what it says that we have 3 desirable properties of a database, and we can only get 2 of them at the same time. The 3 properties are consistency, which means that a data is, when you change something, it's immediately available to everyone. Availability, which means that if I have one node which is down, my system is still running. And then we have partition tolerance, which means that if we split the data in 2 parts, there is still a consistent set of data that you can access. And in the relational model, the SQL model, what we have is consistency and availability with clustering. And in the NoSQL, we have availability and partition tolerance. We don't have this immediate consistency. So it's always, you have 3 things, pick 2. How many times in the architecture and programming we are faced with a trade-off like this, right? When you take this model one step further, you come into a pattern called CQRS. How many of you have heard about it? Good. So actually, you're going to learn something from my presentation. CQRS is an implementation pattern, which basically does is it takes all the data operation that they go to our storage, our data storage, and splits them into 2 parts. The read operations or queries, which do not change data, and commands, or the operations that change data. And what it does, it postulates that each of those different operations should go to different data storage, different database, different system, and they are not mixed. And then, doing this adds an extra complexity to our architecture, of course. We are splitting our data layer in 2. But by doing this, we can optimize each of those, the blue parts or the red parts of our architecture, we can optimize them for different goal. We can optimize the read store for high availability. We can replicate, we can cache it, we can denormalize data. It doesn't matter because we don't have to maintain a single source of truth. We can replicate it. And on the right side, we can optimize for high throughput in changing the data, usually by queuing all those commands and processing them in parallel. So we can, now our database or our storage is not doing 2 things at the same time. It's not maintaining one view of the truth and serving high-performant queries. So we split it in 2, and we get each of those parts is optimized. SharePoint uses this in 2013, a kind of. Just imagine that the red part is the SharePoint content database, and the blue part is the SharePoint search index. SharePoint search index is a read-only store. You can just read from it. And when you have a content search web part, it goes to the read storage. And when you have a content query web part, it goes to the underlying database, which is read-write. So that's why you have a limit to performance of the content query web part. Because actually, if you are doing too many queries, you are locking the database for changes. And that's why now the recommendation is to use the content search web part, because it goes to another data store. Okay. Another technique you can use, even if you are in a relational model, is sharding. Sharding means partitioning or splitting your data across different databases or different storages of the same type. Usually it's done using a partition key or a column or set of columns that act as a unique key for determining where your where your query has to go. In SharePoint, we are familiar with this in Office 365. The tenant ID acts as a partition key because all the data for a tenant are stored together. And in this case, partition key is a tenant ID. If you use table storage from Azure, you have to use a partition key because it uses it to achieve high-performance operations. If you are using a relational database for this, you can use SQL Azure federations. It's a mechanism in SQL Azure to automatically shard your data across different databases. So you avoid the limit of the maximum size of the database in SQL Azure, and you get automatic partitioning and repartitioning of the data. The tricky thing when you have shards or partition data is what happens when you want to list all the tenants? Well, you have to do parallel queries or things like that. It gets a little bit trickier, but it's a small price to pay for having the data partitioned, because usually what happens is when your app goes to write something or to read something, usually all those queries are related to a common set of data. That's why the partition key is important, because if all the tenant operations are stored in one database, one tenant doing high load of changing the data doesn't block another tenant because they're stored in different databases. Okay. I'm going too fast, slow. Okay, good, thank you. Okay. If you just take away a couple of things from the session, just to think about your app architecture, then I'm really satisfied and this session has had a value. Another characteristic we can use to reduce bottlenecks, waiting in a queue. Nobody likes to wait in a queue, right? But what happens is, if we are not using queues, we have request-response model, which is the basic model for web apps, where basically you have a request and somebody fulfilling this request and writing or getting a response. So what happens is, well, this doesn't scale well, because if you have concurrent requests, you need as many shop attendees as concurrent customers you have. So if not, then you have to wait in a queue. And waiting in a queue is sometimes it's good, sometimes it's not. So if you want to scale request response, it scales to a certain limit. You add more worker threads. But there is a limit to this. It gets expensive really fast. What if, instead of waiting for the response, we write the response to a queue and then forget about it until we get the response? If we queue the requests, we have more control. We are decoupling. It's not synchronous anymore. We don't wait for the response. We can look at the size of the queue of the incoming petitions, and we can do retries. If one node fails, we can just read again from the queue. Then we can also see if there are many outstanding requests in the queue. We can fire up new instances of the backend to process the increased load. We can also detect fake requests in the queue, and we can avoid the distributed denial of service attacks, the DDoS, because we are not, by issuing a request, we are not blocking the backend. We are just writing it to a queue, and we are going to get a warning from the queue. And we can also handle auto-scaling of our application. If the queues, the number of requests in the queue is small, we shut down a couple of instances. And if we have more load, we fire up a number of instances. In Azure, we have two kinds of queues. We have storage queues, which come with a storage account, and we have service bus. It also has concept of queues. But the difference is storage queues is like the IP, the TCP and IP protocol. The IP stuff is just point-to-point, and it doesn't have to care about ordered messages, first in, first out, things like that. It doesn't have to care about transactions, canceling things. It passes the messages from one end to another, the couple, load balanced, but that's it's a simple model, highly performant. If you need something like a centralized queue where different parts of your application hook into, maybe you need a service bus. Service bus is a higher level construct. It's a messaging framework. You can add WCF to it. You have publisher-subscriber model, not only queues. You have transaction support. It's not as performant as a storage queue, but it's a must if you, for instance, have transaction requirements. So you have to choose between one of those two queues or use both. Of course, Azure storage queues are cheaper. And if you see a queue basically is a storage account where you can define queues, and usually you will have two parts of your app. One acting as submitting the request in the queue, and another part of your app, the backend, processing those requests from a queue and usually writing to another queue or to another storage with the data that has been processed. The tricky thing is how you notify the user or the front end that the request has been fulfilled. Well, you can use Signaler, the messaging framework, to notify from server to the client, or you can just retry, you can send an email. Usually, it's not such a big problem. So queues are good for decoupling requests, and if you decouple, you automatically get more throughput. Okay. I promise this is the last theoretical thing before a demo, the async. What async does is it also decouples us from the request and response. But I'm going to illustrate it with a short story. Imagine that you go to a restaurant and you have two waiters waiting for your order. One is called Mr. Sync, and the other one is called Mr. Async. Mr. Sync goes to your table, asks you for an order, and you want a stack and with a side of fries, right? He writes it down, goes to the kitchen, goes to the cook, says, okay, table 5 wants stack and fries. Okay. Cook begins to make the dish, and Mr. Sync is doing this. Looks at the cook, doing nothing, is idle, until the response comes to him from the back end, which is the cook, and then he goes to the table, says, here you are, sir. What happens if we have another request? Well, he's busy looking the cook. And there is another waiter, Mr. Async, because the restaurant had some problems because they needed too many waiters. And they said, this guy is recommended because he's much more efficient. What he does the same. He goes to your table, takes an order, goes to the kitchen, tells the order to the cook, and then he writes the table number down, leaves the paper, and goes to serve another customer. And when the cook has finished with a stack, he leaves it there, notifies the waiter. He comes there and says, okay, this was for the table number 5. Okay, here it is. And the same waiter can do many requests because he's not blocked. This is something we take for granted in a restaurant, because if not, it would be a good restaurant for reducing the unemployment rate, having hundreds of waiters, but it would be really expensive. The same thing happens with our scalable architecture. We cannot allow for so many waiters. We cannot allow for so many threads serving the requests. We can do it less. And that's where async comes into place. So the same story, but explained in computer terms. We have a web tier with a work in process, one thread serving the requests. And we have a data tier, where is the data that we want to serve to the request. Then we have a request, thread passes the request to data tier, and then another request comes. But we cannot serve it. We are locked, waiting for the answer from the data tier. So he has to wait. What happens when the data comes back? The request number 1 is served, and now the request number 2, if it hadn't timed out yet, can be served. So it has to wait in a kind of a queue, usually the IIS. If we do this in an async way, same thing happens until the request is passed to the data tier. And then we leave a bookmark of a kind. Another request comes in. The thread moves to dispatch this request, issues another request to the data tier, and leaves a bookmark. Data tier returns the first response. It's picked up by the thread, and it's delivered as a response. So the same thread has done 2 requests at the same time. Why? Because this thing is only possible if you're waiting for something other than yourself. If you're waiting for a data tier, service call, if you're waiting for background operation. But if you're waiting for something that is CPU bound, such as calculations, then async is not going to help you. You have to use parallelism. Because what happens is when I talk to developers in my company, usually they mix multi-threading, parallelism, and async. They're different. You can do async with only 1 thread. JavaScript does this. In JavaScript, the JavaScript runs in a single thread, and you have async calls, AJAX calls all over, but they get serialized in a single thread. If you have multiple threads, usually it's better if you have multiple cores, but for me, it's important to transmit to you that async doesn't mean multi-threading, and multi-threading is good for CPU-bound operations, and async is good for I/O-bound operations, or waiting for external resource to become available. Why we are not doing this every day? Why we are acting as the Mr. Sync waiter, the inefficient waiter? Because it was really difficult to do this in .NET until .NET 4.5. Because you would have to write a callback, and then your code got split into 2. The async operation and the callback when it's finished. So it's kind of spaghetti code by design. And using async await, .NET does the heavy workload for you. They keep the track of the outstanding callbacks, so you don't have to. Basically, it's an interesting reading how async await works under the covers, because it builds a state machine, but it would require another session to explain that. So let's go to see what happens when we use sync versus async in a back end of our application. So I hope you are still awake, because I know that having a session after lunch is always tricky, because all your energy is digesting the food, but I hope that you still have some energy for following the example. Okay, what I have here is a kind of simple controller that gets a list of stock information. Stock information is it's a simple class with a stock ID and a current price. And what we do, we go to external system, which is the table storage in Azure. I will also show you this. I have tables. I have one table called quotes. And if I query the table, I can see that I have, remember the partition key from our sharding example? Well, I'm only interested in stock. So if I have another application accessing the table storage, I split by partition key so we don't get mixed. And I can do whatever I want here. So I'm going to read from this table storage, return all the information about stocks, and then create a list of stock information and return it to the view. Okay, simple. It's synchronous because it blocks until this execute query operation finishes, but it's simple. It's easy to understand what it does. So if I try this, I have used web API, so I go to API/stock, and get a JSON object with a stock information. Good. What I have to do now is to see how performant is this. So I get the web API endpoint, I go to Azure benchmark, and I do 500 requests, 100 requests at a time to this endpoint. Be patient, working on it. 100, 200, 300, 400. Okay. Now we have a couple of interesting keys here. We have effective throughput of 40 requests per second. No, this tool comes with the Apache distribution, with the Apache server. So I use this tool called XAMPP, which is basically a standalone executable file that you get the Apache and all the tools inside. So you can I don't have to install things on my Windows operating system. And we can see that the mean time per request is 2.4 seconds, each request. Why? Because usually they are waiting in the queue, but it's really slow. It's 40 requests per second. I have another version of the same controller called async controller. It's the same. I use async. Instead of returning a list of stock information, I return a task, because if we want to use async, we have to change the return types to task, or a task with a generic type. And then I use the same exact same code as I did in the synchronous version, except for this. Execute query segmented async. It's an async version of the same call. So I just say to the table storage, give me everything, but give me this query in a non-blocking way, async way. And I will await for the result. And then I do the same. I build a stock information list and return it as a JSON result. So now I will repeat the same thing to another endpoint, stock async. Same infrastructure, same code, same data, same Azure storage. 1, 2, 3, 4, 5. Well, usually it's not that big a difference. It's like 10 to 20 times faster, but I'm really surprised that it's been so fast. So we have 422 requests per second. Same code, same infrastructure. That's why if you build an API or a backend, it should be async by default, because you get multiple requests at the same time, and all your worker processes are busy serving requests and are not idle waiting for the request to come from the backend. But when I was choosing the demos for illustrating those points, this is as a big eye-opener as I could find. Like, with the same code, I get 10 times the throughput. I even tried to do this in a JavaScript version, but the problem with the JavaScript, I had to use web workers, and you get just as many web workers, which are threads, but it also does the same thing. But the benchmark tool is much quicker. You will get the source code if you want to check how it's being done. Okay. So, don't worry, we'll be finishing soon, because I only have one guideline to share with you, which is the redundant design. The redundant design is a tenet that says that if one node of your application or one instance goes down, your application has to keep working, even if you had some delay. like those notifications, we are experiencing technical difficulties. Please be patient. It may be slower than usual. So when you design for redundancy, what you do is you duplicate all the components of your application. But there are additional things you have to take into account. It doesn't help just duplicating things. You have to design all your operations to be, I'm sorry for the ugly word, idempotent, which basically means that it doesn't matter how many times I retry the operation, I still get the same result. For instance, querying is usually idempotent, because if I query for a username, I get the result. I query again, I get the same result. I query again, get the same result. But doing bank transfers is not. I subtract a quantity from one account and I add it to another account. If I repeat, the amount of the money in the first account is going to be depleted over time. So how do you do this if you are doing a banking application? Well, you add an extra parameter like transaction ID, so you check if this transaction has already been processed. So then you don't get this different results if you retry. Because with redundant design comes retries and failovers, which means that your application eventually has to do things twice. So you have to plan for it. And when you duplicate your components, you also have to balance, do some load balancing across all those instances. So you don't channel all the requests to one machine or to one instance. So there are several load balancing mechanisms you can use, or different policies that you can use. And here we have, in Azure, we have a nice little tool called Azure Traffic Manager, which is basically a balancing solution for your app sitting in Azure. What it does is, I'll try to draw this, basically it maintains a table of the states of your application. You have 3 different instances, and your Azure Traffic Manager monitors those instances. You have to add them in the table, and it keeps polling them every 30 seconds to see if they are alive. And it keeps maintaining the metrics like response time, things like that. And then, when your application issues a request, it goes to the DNS, and in DNS you have to define that Azure Traffic Manager is your endpoint. Your request goes to a traffic manager, and then the traffic manager looks which of your servers is the most appropriate one, and then returns the address of that server. Sorry about that. And then your application goes to this. You have a round trip, but you are rerouted to the appropriate server. So this is how you can leverage Azure, so you don't have to build your load balancing mechanisms all by yourself. The only thing you have to define is a simple URL, which is going to be hit by the traffic manager every 30 seconds. So it keeps track of, if it gets anything but 200 status from the HTTP request, it's going to mark it as a fail, as this instance is dead, and it's going to try again 30 seconds later. Okay. Not only the SharePoint apps or Azure apps are built redundantly. We all know Farmville, the game that was famous in Facebook a couple of years ago, where everyone was doing farming, and they wouldn't do it in the real life, right? And this is the architecture of Farmville application. As you can see, it's redundant from the DNS servers to the data storage. There is a white paper about Farmville design, also really interesting how they designed for scalability in the first place. So they just made everything redundant. Okay. I'm going to summarize quickly what I've been talking about. Basically, if you want scalable apps, if you just don't want any kind of apps, but highly scalable apps, you have to change the architecture. You have to make an architecture a little bit more complex, but you get increased response, you get increased load, you get satisfied customers, you get millions of users, and you never get the dreaded message that the server is not ready please try again. And you avoid the Death Star explosion. Everything just for the price of changing the architecture. And you have seen that there are 3 guiding principles for building scalable apps, and they translate at least into 7 tenets for building highly scalable apps. So again, this is the summary, and if you remember this from all the things I've showed in the session, if you remember this, then I'm glad. It has served the purpose. If you want more information about building apps on Azure, I've chosen a couple of sessions that are complementary to this one. Yesterday, Kirk Evans was delivering a session about building SharePoint apps with Windows Azure, Platform as a Service. And he showcased how to use queues, how to use background processing. So his application was a kind of scalable, but his focus was on showing you how to build the actual code. And my session is more about why you do this in the first place and why it's important. There was also a session this morning by Bob German, developing cloud-hosted apps with MVC5, how to build MVC5 apps in SharePoint, also covering some of the things that are important for scalability. And at the same time as this session, Advanced Development Patterns for SharePoint Apps by Nathan Miller. But this is not all. We have additional resources. In the bookstore that you get in the registration area, there is a little book, it's like this, called Scalability Rules, 50 Principles for Scaling Websites. It's a summary of those guiding principles. There are many more examples of how you can do your scalable design for web applications. It's not directly related to SharePoint apps, but SharePoint apps are web apps at the end of the day. So it's highly recommended. So I've asked for the bookstore to have the books stocked up, so if you want to check it up. There is also a portal called highscalability.com where you can find white papers and articles and additional information and real-world examples of highly scalable applications. And I've also put all the demo code that I've used in my demos in a Bitbucket address, so you can get it from there. And I will also use this as an ongoing scalable app demo. So I will add functionalities. I will add a SharePoint app, which is built from all those pieces that I've been talking about, because I couldn't cram that much information in this session. You're already overloaded with information. So just check it up, and it's going to be updated in the following months. So again, build apps, explore the API, and do it in a scalable way, and keep your customers happy. And where I come from, we have a saying that if you are satisfied with this session, please tell everyone, and if you are not, tell only to me. So, okay, right evaluation. Thank you very much. And if you have questions, come here. I have some swag to give away, so you're more than welcome. Thank you.